fact, we promised to make one session each month, but this month was very special. This is the second session for today, but because it's important topic, so we need to make this session and to give the time for our guest to speak freely about this topic. Today we have Giuseppe Bonaccorso with us. I think there is no need to introduce him to you. He is right now, he's the second time together we are here on this event. Welcome, Giuseppe.
Thank you, Ghaith, and welcome to everybody that has joined the meeting. Very glad to be here.
We are glad also. Today the session, it will be focusing on reinforcement learning. And before starting and giving you the time to tell us about this topic, I have one question here to start with it. We used to categorize the machine learning on three categories: supervised, unsupervised learning, and then there is the reinforcement learning. And today also there is some other topic appeared, just like self-supervised learning or semi-supervised learning. What's the meaning of this categorization and how we can understand it?
Well, yeah, this categorization or taxonomy, as you said, is, we can say it's artificial. I mean, it has been created in order to define the different strategies that are adopted in each training approach, or in each learning approach, to be precise. Clearly, we need to understand one thing. First of all, the background of all of them, or at least of all but one maybe, is a learning problem. So I have a definition which is not very, very academical, but it can make you understand the problem. You have a problem that can be a question, and imagine yourself in two instances, T0 and T1. In T0, you are not able to solve the problem. In T1, you're able. What happens in between is the learning. The way you learn, the way you transform yourself, you change your mind, you learn something, is categorizable into different ways, different approaches. And exactly as you said, supervised learning, semi-supervised, self, are very, and in particular, reinforcement learning, of course, that is the topic for today, are very specific to learning. Unsupervised learning is probably the less learning. I mean, if we compare the way we learn through the other processes, unsupervised is more a discovery than a learning, because it's more an understanding how the data is structured. But we can consider unsupervised learning also a way to learn, or to extract some features that are important for learning.
This has pushed me for the second question right now, because for reinforcement learning, as I understand it, it's more experiencing, not than learning, more than learning. So because we are getting the reward from the environment, we don't have, let's say, it's not labeled data somehow to just to extract the features from it. So is it like this, or it's different?
Yeah. Absolutely.
First, just I will ask everybody to mute themselves, and then we will open a window for question at the end of the session, please. Thank you, Muhammad. He mutes his mic. Sorry for that.
No problem. We need to say one thing. First of all, in nature, the most diffused way of learning is reinforcement. It's impossible to consider supervised learning when we talk about animals, for example. The reason is obvious. In supervised learning, you have precise data, you have labels, you have precise relations, which are absolutely impossible for the majority of problems that animals have to face. Whenever I talk about reinforcement learning to an audience, I generally ask one question. I remember once there were a very large audience, and I said, I can pay a month of salary to everybody that can come here and can tell me exactly how to ride a bicycle. But I don't want to say, I want to listen to a description I want to know exactly the forces that you apply to your muscles, the moments, how you keep the balance. And clearly, nobody is able to do this because we learn in a very fuzzy way. So you're right in saying that it's experiencing, but on the other side, it's the only way to manage problems that when are transformed into mathematical structures become extremely complex. So complex that it's almost impossible to solve them in real time, even sometimes with a powerful computer. So reinforcement learning has this particular ability that we are going to discuss, to learn everything just thanks to the experience. And there are some particular situations that we are going to discuss that are very characteristics for reinforcement learning.
So the time is yours, and I will stop my video, stop my mic, and I will enjoy with the audience to your presentation.
Thank you very much. I'm sharing my screen. Let me, okay, just please confirm that you see my screen. Can you please confirm, Ghaith?
Yes, we do. We do.
Perfect. So thank you very much. I hope to entertain you all. As you can read, this is a crash introduction. So it's not an introduction nor a course. It's a crash introduction because the time is limited. The topic is very, very wide. But I want to introduce the readers of books, the students, and whoever, the practitioners, whoever, to reinforcement learning, giving the most important elements and giving them the sparkle to continue exploring with a little bit more awareness, hopefully. And of course, I want also to answer your question. We must be precise. I put a warning as first slide because I know that there are some people who want a very strong mathematical rigor. Unfortunately, in this case, as it is a crash introduction, I have to say that sometimes I need to skip some mathematical rigor and some topics are discussed only very briefly. This is because of time, of course. But in the end, I will give you references and Ghaith will send you a list of books and also a list of source codes to test the examples that I will show you. So, sorry. So the agenda for this introduction is split into these elements. I want just to talk 1 second about the first one, because it's very important to understand the constitutive elements of any reinforcement learning scenario. All the other points are algorithms, are ways to achieve the goals, but I don't want to spend time now. But it's important to understand that as in supervised learning, there is a sort of setting where you have a data set, a training set, validation set, test set, and so you have a structure. Also here, we have some specific constitutive elements. The only problem is that these elements are very interconnected. So if you try to understand them using a sort of a circular diagram or something like this, you will find out a lot of connections and you can get crazy. So it's easier to talk about the elements, and when there is a reference, just introducing the other elements and then expanding them. So this is the way we are going to do. So let's start. Sorry, before we start, as Ghaith said, please keep your question for the end, because otherwise we risk to remain stuck if there are questions in the meantime. And so it's better to go till the end. So the first thing to say is, of course, that in reinforcement learning, we have an agent. An agent is a generic term to identify the entity that can be an animal, as we said, can be whatever, can be a computer program that plays Atari games, can be a self-driving car, can be a robot, can be whatever. The entity, this entity acts into an environment, which is another element that we're going to discuss in the next slide. And the goal of the agent is clearly to maximize, or first of all, to achieve an objective or a sequence of objectives. But to achieve these objectives, there is another medium that we have to consider, and this medium is called reward. In other words, the objectives can be achieved only through a maximization of the total reward through a process that we are going to discuss. The reward is another peculiar element, and we'll dedicate a slide to this. That is the feedback that the environment provides to the agent. But we are going to discuss all these elements in the next slide. As I said before, there are so many interconnections that it's very difficult to explain one single element without referencing the others. There are some peculiar elements to say about the agent. The first one is a very interesting thing, because in all problems, we suppose that an agent can repeat the same experience an indefinite number of times or an infinite number of times. In other words, the algorithms can converge if we assume that the agent can repeat for a very large number of times. This is clearly non-realistic, because, in reality, you cannot repeat the same thing so many times, in particular when there are dangerous situations. But this particular condition is a consequence of the fact that also in the nature, the agents learned to manage the danger in a particular way. I will make an example in the next slides. But you have to remember this, that the agent can repeat every time it's necessary. There are no limitations. If you put a limitation, the convergence cannot be achieved in some cases. The agent operates in a time sequence. In general, the time sequence is discrete, but it can be also continuous. Just for simplicity, it's easier in many cases to consider a time sequence of discrete instance, but it can also be a continuous time sequence. And the agent has a set of actions. Also in this case, the set of actions can be discrete or can be continuous. Imagine that you have the possibility to move in a checkerboard environment, as we are going to see, and in that case you have 4, 5, 6, a certain number of potential actions. But imagine that you are a robot, and so you have to control the direction. So theoretically, you have an infinite number of possibilities, though the value is continuous. But there is at least a range. I mean, in general, the set A is a set of with boundaries. It's not an infinite set. Moreover, as I said before, we consider in the next slide, we have a more detailed description, a specific expected reward that in general we indicate in the instant after the action. So whenever the agent performs an action at time t, we expect a reward that conventionally is put at time t plus 1. So it's just a convention, because it's possible to say that the reward is exactly at the same time of the action, but conventionally we always put the reward in the time t plus 1. Moreover, and we are going also to discuss about this, the environment is a sequence of states. So the state is a certain situation, a certain setting where the agent can be. And in each transition, every time the agent does something, there will be a transition. The transition can be self-referencing, so the action can be do nothing, and the agent, in that case, will remain in a certain state. But in general, whenever an action is performed, there is a transition from the state t, st, to the state at the instant t plus 1. So let's start with the environment. The environment is the counterpart for the agent. So whenever an agent performs actions in the environment is a very abstract entity that has a main responsibility to provide feedbacks. And the feedbacks are exactly what I answered to Ghaith, are a way to communicate if the action was positive or negative, and there is generally a certain degree of positive and negative. It can be very positive, very negative, and so forth. Imagine when you are touching a surface that is hot, you can receive different feedbacks according to the temperature. And it's something like this: it's very hot, or it's just hot, you can keep your hand on, or it's extremely hot and you have to remove your hand immediately. These feedbacks indicates immediately how the action should be evaluated by the agent. Now, let's move on the characteristics of the environment, because in the next slides we are going to discuss exactly the actions. But the environment can be modeled in two ways. One is a deterministic way. A deterministic way is very simple. It's just a function. So it's a function, it's a pseudo function, because it's a vectorial function, because it takes two parameters, takes the state and the action, and returns the next state and the reward. But every time you apply the value st and at, you will receive always st plus 1 or rt plus 1. So the time in that case is useless, because in other words, there's no more evolution over time, and this represents situations where the environment, we can say, has no surprises once it has been discovered. However, in reality, deterministic environments are very, very, very rare. The reason is that there are so many latent factors. There is noise, there are factors that we don't know. So it's much easier and much better to model the environment in a stochastic way. In a stochastic way, we don't have anymore a function returning a couple of values, but we have a transition probability from the state st to the state st plus 1 with index I indicating a certain state, one of the possible states, given the action at. So when the agent performs the action at, we have here a vector of probabilities. And each of these probabilities represent one of the possible further sequential states. So in other words, in this case, we are not sure that we are going to transition to a certain state, but we can have a probability. Just to make an example, imagine that you have like a door, a plastic door, you know, the plastic cover, for example, and you press with your finger, and you can expect to, after pressing, to create the hole. But with a certain probability, you can also discover that you have just deformed the surface because your strength was not enough. So there are different possibilities, different actions that can happen with different probabilities, of course. And they are, of course, related to the actions. This is extremely important to consider, because this is the representation summarizing what we have said and what we are going to discuss more. So the agent acts in the environment, performing actions indicated with A. the environments will answer. And you will see this, this is like a feedback cycle. So a classical feedback cycle. The agent has the responsibility to change the way to perform actions given the states and given the rewards. But indeed, the states are just situations. I mean, we can imagine it this way, while the reward is a measure. So in general, the agent will consider the measure of the reward as the most important element to evaluate the action. Now, I need to jump to clarify a concept. I don't know the background. I suppose that each of you have a background of computer science. However, I suppose that you have certain knowledge of Markov chain. A Markov chain, I just summarize very quickly and in a very dirty way, is a process where you have a certain number. Suppose we have a discrete distribution, so you have a certain number of states, and so you have a transition matrix where each element of the matrix is the probability that when the chain is in a certain state can transition to another state. In this case, in a Markov chain, the transition is autonomous. So you move from state 1, 2, 3, 4. There is nothing in between. In this case, instead, when we transition, when we are in state 1, for example, we apply the action 1. So we do something, we make a decision in that state. This forces the system to transition to another state that we call state 2 and to provide a reward. And again, we apply a new action and the process is repeated. So if you remove the block A1, S2, R2, and you consider S1, S2, Sn, you have a simple Markov chain. But if you include the action, so you interleave the transition between states with actions, you get what is called in a very, again, I repeat, sorry if there are mathematicians, don't shoot me, a Markov decision process. The decision is encoded into the actions that we are performing. Now, this is one of the most interesting concepts, rewards. What is a reward? First of all, reward is a term indicating a generic feedback. So a reward doesn't mean positive reward, can either mean positive or negative reward. Conventionally, instead of saying reward and penalty, for example, we always say reward. So you don't have to imagine that a reward is always positive, as normally we imagine. Now, let's suppose that we have a transition. So we have an immediate reward. And an immediate reward is what we can also call the shortest horizon, because you have to consider a sequence of actions. And the example in this case is that you have to reach a destination that is in front of you. So you know that the shortest path is to go straight. But unfortunately, in the middle of the street, there is a big hole. So if you go straight and you don't consider the hole, and you consider only the immediate reward, till a certain point, you will discover that the immediate reward is positive, but then you end up in the wall and in the hole, and then you need to, or it's the same for a wall, you have to exit from the hole, and you take some time. So the shortest path probably can become very long. So it's more helpful not to consider a very short horizon, but to consider a longer horizon. So to consider, in this case, the sequence, the infinite sequence of all rewards that we can get from the first moment till the last one. Now, don't worry about this infinite sign here, and because I will immediately tell you why it's infinite. It's infinite because we want to prove one thing, but in reality, this sequence is always limited. So we never have an infinite number of rewards, but in general, we have a certain number of rewards because any sequence till the starting from the first state till the ending state can have 10, 100, a million, but a finite number of states. But of course, the immediate rewards are more important than rewards that we can get after, I don't know, 100 steps, because we can change strategy throughout. So we use a discount factor, which is normally, it's bounded between 0 and 1. It must be bounded between 0 and 1. Clearly, if the discount factor is equal to 0, this sum will become just RT plus 1. So the total reward is just immediate reward. While if it cannot be 1, because 1 will create this infinite sequence, but it can tend to 1. And in that case, we are giving a weight to all the rewards in the sequence. So all the rewards, so the value will become more and more bigger and bigger, and the rewards which are far in the future will become more and more important. However, if we just consider that all rewards are in absolute values bounded, it's easy to prove that this geometric series that is obtained by just putting the inequality and putting the Rmax out converge. This is a geometric series, and you know that the sum of this geometric series, if gamma is between 0 and 1, and cannot be 1 because, as you can understand, if it's 1, this will become infinite. But if it's bounded between 0 and 1, the total reward will be also bounded. In general, in all applications, when this sequence has not an infinite number of values, we use gamma, for example, around 0.7, 0.8. These are reasonable value to have, let's say, a middle, not very long, not very short, but a good horizon. But in general, you should avoid a very long horizon, like 0.99, or a very short horizon like 0.1 or 0, because in that case, you risk to have a system that cannot create long-term strategies. Now we arrive to the main problem. Indeed, reinforcement learning can be summarized in finding what we call a policy. Any solution to a reinforcement learning problem is to find a policy. A policy is the simplest thing that you can imagine, because a policy is simply a function or whatever, I mean something like a function that, given a state, can suggest the agent which is the best action to perform. And just like for the environment, we can have a policy that is deterministic. In this case, you say, in this state, go right, in that state, go left. It's just like when you give directions, for example, to reach a place. When you see the traffic light, go on the right, and in that case, it's just a deterministic policy. But again, policy are extremely difficult when they are deterministic to be found, given the lack of flexibility that we have. That's why we prefer to model the policy as a stochastic policy. In this case, it's just an array, a vector, where each element is the probability of taking that action, or the goodness. You can consider this value between, of course, the sum must be 1, but each element can be considered like the goodness or the probability in terms of goodness of the action in that particular state. So, of course, an agent, this is an observation that has, for example, 5 actions, and each of them has 0.2, means that has a total uncertainty, because it doesn't know what to do in a particular state, while an agent that has 5 actions and one of them is 0.9 and the other ones are 0.0002, 0.25, well, in that case, we'll select an action with the maximum certainty. That is the goal, because the goal is to find a policy where we are sure to select the best action in each state. Now, a problem. This problem is very common, and it's called exploitation versus exploration. Because whenever we work with reinforcement learning, when normally we use a stochastic policy, from now on, we always refer to stochastic policies and stochastic environments. We can do two things. One thing is exploiting the learned policy. So in other words, if the policy is going to be learned, so it's a process. Meanwhile, you learn the policy, you try every time to select the action which has the highest probability. This is exploiting. But if we do this way, we risk to end up in a situation where we don't do the other option, which is exploring. In other words, we are going to do always the same thing. The exploration of the environment on the other side is possible only if we perform actions in a suboptimal way. So in other words, is just like imagine that you have to go to work, you are walking in the street and you know that a certain path is the right one, but one day you decide to take another street. You can discover that the other street is longer, but you can also discover that the other street is shorter. You can do this only if you explore, even if you have already a policy that helps you exploiting. So what we do is to use a so-called epsilon greedy policy. This epsilon is a simple parameter that initially is kept very high. In other words, is kept close to 1. And the policy is structured in this way. Initially, when the probability, this is a probability, P indicates a probability. So epsilon is close to 1, we sample. And so when epsilon is close to 1, we just select a random action from the policy. Meanwhile, while we go on, so while we learn, after a certain number of iterations, so the limit in this case, just to be formal, of epsilon t is 0, we reduce epsilon, because after a while, we are sure that we have explored the environment, we know how the environment is structured, and at that point, we can instead move to a stronger selection of the best action. And in that case, we use the argmax. So we select the action which is associated with the highest probability. This is a standard way that is normally done in the majority of cases. So at this point, we start with a discussion, and I will be a little bit faster now because I want to focus on the algorithms. But before moving to the algorithms, we need to understand one concept, which is the value of a state. To answer this question, first of all, we have to understand what is a value. A value, in this case, should represent the goodness of being in that state. But the goodness, again, cannot be evaluated considering that state autonomously, but also considering what we can do starting from that state. So the inventors of this theory had an interesting idea. They said, well, it's quite simple. We can imagine the value of the state given a certain policy. From now on, we have a policy as the expected value over the policy. Now I explain you a little bit better, of the return, starting from that state. So in other words, they said, if I am in a state and I have a policy pi, I compute all possible sequence of returns. Of course, in this case, to be precise, the summation is to infinite, but in reality is limited to a finite number of sequences, of steps. I consider all possible sequences and I average them. This is the value of the state. And it's quite reasonable because In other words, it's the way to say I am in a state, I have a certain number of possibilities. If I have some possibilities that will drive me to reach a good point, so where I have a reward or I reach a final objective, well, the state is good. If instead all around me there is the desert, and on one side there is a lion, on the other side there is a crocodile, and so forth, probably the state is not good. So it's an average, is an expected value over pi. Here there is a very not complex, but there is a proof that if we evaluate through a process called the value iteration the states, all the states, so we iterate this process to find out the states of each, to find out the value of each state by iterating, we learn both the policy and we learn an optimal policy, because we learn the policy and we learn the associated states. The real problem is another. I think that some people have already understood that the problem is this expected value, because in every situation where I have to consider all possible actions that can I perform, and I have to evaluate all possible sequences. This is extremely unpleasant, because in general, I don't want to do this kind of job, and in practice, it can be extremely long. That's why an idea has been proposed, which is the most important idea that will be developed also in the many other algorithms. I'm omitting here any proof about this, but in the references that I'm going to provide you, there will be the formal proof that you can iterate this is called value iteration, and this will converge. This is the value iteration. I want to be faster, as I said before, because it's a very, probably it's not the most important algorithm in our case, but what we do in this value iteration is just to make you understand, because the dynamics is always the same, is updating the value of a state by selecting, performing, first of all, this summation of all possible states, of possible states around the state where we are. In other words, all possible successors of this state. This first term is the transition probability given all the actions. Again, I repeat, you have to consider all the actions, and this is a burden. And the transition probability represents a weight, in other words. So this is a weighted mean. You can consider this a weighted mean. And it's quite simple, because this is just the immediate, this is the expected value of the immediate rewards given all possible actions, plus the value starting from that point on. So the process is obtained through a technique called dynamic programming. Some of you probably know this, but in practice is like splitting the sequence into small steps, and in each step we evaluate what we can get. So this term determines what we can get, the expected return that we can get, and we sum the value that has been accumulated till that moment. Once we have completed this sequence for all possible successors, we update the state, and we repeat this process. But in this process again, we have the sum of all possible successors, and we have to consider all possible actions, because if we don't consider all possible actions, this sum will not be possible, because we have to select the maximum value given all the actions, because as you remember, we want to find the optimal policy. So we want to find the value that is the maximum one, because the maximum value is the value associated to the optimal policy. It's like a circular loop where the optimal policy will lead to the maximum value for that state. It's possible to prove, but we are not going to do this because honestly, it's quite complex, that if we repeat this process an infinite number, not an infinite, a certain number of times, this will converge to the optimal policy. And when we say the optimal, it means that it's not possible to find a better policy. But please, this is only if you want to go deeper to this. I strongly suggest to read about this because this is extremely important. But for our discussion, we are going to focus our attention on this element that you probably know, you probably read about this, the Q function. The idea of the Q function is quite simple. The state is extremely difficult to manage. So even if everything is fine, everything converges, everything is perfect from a mathematical viewpoint, in practice, a state itself associated with a value is not helpful. So we need to find something more. And that something more is to have a function that, given a state and an action under policy, can help us in understanding which is the most helpful thing to do. In other words, the Q function says if you are in the state st and you perform the action at, you will get a value, I don't know, imagine 10. If you are in the same state and you perform another action, you get 2. So it's easy to understand that it's preferable to select the action, the first one, and not the second one. In this case, the situation is exactly the same as before, because we need to compute an expected value under the policy pi, but in this case we are fixing the action. So this is much easier to compute, because in the previous case the action was not a variable, so it was in the distribution. In this case, it's fixed. So once we fix the state and the action, we have just to evaluate in a precise state and performing a certain action, we have to evaluate the expected value from that state on. So the expected reward from that state on. We are going to see how this Q function can easily be computed and how this Q function will help you in finding easily the best policy in a lot of situations. Just for your knowledge, it's also possible to do this, to do the same thing that we did before. That this is called Bellman equation. Bellman is the inventor of dynamic programming, which is the technique of splitting into blocks and performing this sequential optimization, we can say. And the result is exactly the same as before, but in this case we are not, if you remember, before we had this max because we had to select the action, in this case with the maximum value. In this case, as the action is fixed, everything is simpler. In this case, this transition probability is simpler, this expected value is simpler because A is fixed, and clearly it's just a summation. But in general, we are not computing this because we are using other strategies to find the optimal Q value, which are more effective and easier. And remember, this is a crash introduction, so I'm sorry if this part is not covered in detail, but this part is generally very cumbersome otherwise. But it's easy to understand that given a Q function, we can easily obtain a policy, because the policy, in this case, k plus 1 is just for indicating an iteration of policies. So if you remove these elements, k is just the argmax of the Q function given the argmax with respect to the action. So the policy in this case is simply, I have the Q function, I learn the Q function in some way. So I just observe the state, I check which action maximizes the Q function, and I select that action, nothing more. This is possible to prove, and clearly I omitted the proof, but there is a theorem called the policy improvement theorem that shows that through the iteration of this mechanism of the iterating the policy, so performing this process iteratively, it's possible to find an optimal policy again. Again, when I say optimal policy, I mean that there is no better policy. So there is no way to find, or there is a better policy does not exist at all. Let's start 1 second. We are here now. This part was a little bit more theoretical. Now let's move to some more practical, showing in a more easier way, to how to obtain a policy. And I will show you some examples. The first example is a very simple one, and it's called the time difference or TD algorithm. This algorithm is simple, but also very effective, and it's also extremely easy to understand. First of all, I have to say one thing. Here, the notation is a pure mathematical notation. So whenever you see these first two elements here, t plus 1 and t, it's the classical plus equal that we normally have in all programming languages. But here we have to split, so the notation can be a little bit longer. But indeed, what we do in updating the value of a state, in this case, is to consider, first of all, alpha is a learning rate. We are going to discuss this later. First of all, we consider we made a transition. And remember what we said in the initial part. We made a transition at the beginning, exploring, so taking a random action, for example, and then exploiting, taking the most likely probable action. So we observe an immediate reward in the transition from the state I to the state J, and we sum the difference between the discounted difference of the state as J minus the difference of the state I. What does it mean if we look at this? We are at time t. So imagine that you are in a state I and the value in the state I is 10. You move to a state J and the value in that state is 15. So it means, even with a discount factor, that you, in the difference, you have about 15. This is probably a bit less. Let's suppose that is 14, given the discount factor, and this is 10. So this value is 4. So in other words, you had an improvement in moving from your current state to the next one. But you have to sum the reward, because the reward can indicate that the transition was really positive, or can indicate in some cases that the transition wasn't really positive, because initially, in particular, these values are probably random. You don't know them. So initially, these values here have a limited effect. It's helpful not to use, for example, random values, to keep them, for example, equal to 0, because the reality is that if you don't know the value of the state, the only thing to consider is the reward. The reward indicates whether you have done something helpful or not. So if the reward is positive, this term will be positive. If the reward is negative at the beginning, in particular, if this difference is 0, this will be negative. Once the states will become, the value of the states will become more stable, the reward will confirm the transition. In other words, will become a way to reinforce the transition. Now, this is called, this algorithm considers only 2 instances, so a transition from from I to J, and it's called TD0 because it considers only this reward IJ. But it's possible to improve these algorithms using, this is a family, using the so-called TD lambda algorithms, using simply more time steps. So transforming this block, the first block, because the last one is clearly the same because it's the current state, but the first 2 terms in parentheses can be transformed into a sequence considering more steps and a longer sequence of actions that happened. This is a little bit more complex. We are not going to discuss this algorithm because it's necessary to introduce many elements. But in general, a TD lambda algorithm is generally faster to converge in some cases, and it's more precise and faster to converge because it considers more sequences. But it's clearly more complex because we need to analyze longer sequences for every step. In general, TD0 is quite enough to solve almost any simple problem, clearly simple. But in general, it works. And the constant alpha is a pseudo learning rate. I mean, it's a learning rate. It's not proper learning rate, but we can consider like a learning rate, and it's between 0 and 1. Of course, 0 means that we are not considering at all the experience. 1 means that we are evaluating the experience. Consider that if alpha is 1, this term, the first term, and this term will be cut out. So what we get is only this term here. So the time difference become exclusively, in this case, the current experience plus the future value. In general, a good way to estimate alpha is to start from a value which is in between 0 and 1. For example, 0.5 can be a good choice because in that case, we evaluate both the experience, the current value, and the new experience. Now, given the TD algorithm that we have seen before, we can call this term here, okay? This term here, without any other notation, as TD error, as time difference error, because it's a time difference error, is the difference, the error of the difference. A suggestion that has been made to improve this algorithm is called actor critic, and the idea is quite simple. Instead of using a single system having the ability to get an action and to observe a state and to select an action, we split into 2 blocks this system, 2 blocks that can have a different learning procedure. One block is called critic, and the responsibility of the critic is to evaluate the value of the state and to influence, in other words, also the actor. But the actor on the other side has also some autonomy in determining which action should be selected for the environment. So if you see this diagram, the critic will receive the input of the next state, and the reward will evaluate the state and will provide a TD error to the actor, and the actor will correct the action, the policy, to select the best action. You can ask why this is better than a single TD or in general a simpler algorithm. The reason, there are many reasons. The main reason is that this way of working helps also to split into different components that can learn different aspects of the problem. So these 2 models can share a part of the same structure. For example, if it's a neural network, But in general, there are some layers which help in specialization of critic and actor. And then those elements will help in helping in finding the value in a more precise way and in selecting the action in a more precise way. The dynamics of actor critics is quite simple. It's based on simply a greedy policy, which is based on a softmax. What we do in this case is just creating a matrix called policy importance, where each element of the matrix is a state and the action. So given state and action, there is a value in this matrix. It's not a matrix, it's a multidimensional matrix, yes, it's a multidimensional vector, where given a state and an action, you have a value representing the importance of that particular action in that state. And the policy is obtained simply by using the softmax. This trick of performing the softmax by using this subtraction of the max is only because we first multiply numerator and denominator, and then we transform this using the exponential properties, is just for numerical stabilities. But you can, for now, don't consider these two elements, just consider the first one, which is enough. So we have a softmax policy where each element is proportional to this policy importance. Now, suppose that we have a transition from the state Si to the state Sj, and we receive a reward Rej. The TD error is this one that we have seen before. And it's obvious, as we have seen, that if the value Vsi, so this one, is less than this term, the critic considers the action as positive, because it means that what we have done, the transition to J, has driven to a higher value. And vice versa, if it's negative, the critic considers as negative. The goal of the critic is to learn to distinguish immediately, given a state, which actions will help in improving and which actions will instead help in decreasing the value. Sorry. So the critic can immediately update the policy importance. And in this case, this update is done in a very simple way, because you can see that it's just the policy importance is plus equal the rho, which is just a weight, 0 to 1, a classical weight, times the TD error. So the higher the TD error, it means the higher the importance of that action, because the higher the TD error, the larger is the TD error, the larger is the value of the destination state, and the smaller the TD error, or negative, larger but negative, it means that is larger the value of the original state. So the action is very negative. So it's easy to modify this policy importance. The actor now just select the action given the policy, and it does use the argmax. In this case, the exploration is also less important, or I mean, it's important, but it's easier to explore naturally in this case, because if we start from a policy which is a softmax, normally a softmax policy is initialized with a maximum entropy. So all the actions initially have the same value, have the same probability. So when you perform an argmax, you normally just select a random action. So it automatically updates the action so that there will be a peak representing a specific action when the critic has understood that that action is really the good one to select in that particular state. Now we go very fast. I think that our time is running fast too. So I want to talk about these two algorithms very quickly. And then I ask Ghaith about the remaining time. I don't want to take too long. The SARSA algorithm, SARSA is a name that is the classical example of Occam's razor applied to a title of an algorithm, just means state, action, reward, state, action. It's a very simple name, and it's a natural extension of TD0. But instead of using the value, we use the Q function. So given this transition that you see SARSA, if you read, given the transition from T, ST, we apply the action AT, we obtain the reward T plus 1, we transition to the state ST plus 1, and we get the action AT plus 1. We can easily rewrite the previous equation that we have seen before, the TD0 algorithm, so you don't have to learn anything new in this case, but using the Q function. So in other words, instead of using the values which are, as we have seen, which are a little bit more complex, we can use the Q function directly. And in this case, this is again a plus equal. Remember what we have said before, if alpha is equal to 1, these two terms go away. So the past has no more importance. If alpha is very is in between, we can balance. So we have the immediate reward plus a gamma, a discount of the Q function, given a potential AT plus 1 action. This one can be a random action in case of exploration, or can be an action selected using the exploitation, so the argmax. And that action is selected for determining the Q value. Now, I invite you to pay attention to this term, because this term, this particular term, is the only difference between this algorithm and the next one. It's easy to prove, but of course out of the scope, that this algorithm can converge, and can converge in, we say, with probability 1. Don't worry about this. We don't have time to discuss this concept, but we can say that converges. The only thing is the learning rate should decay. In other words, the sum of the learning rate can be infinite, but the sum of the squares must be finite. This is true for the majority of learning algorithms. In reality, we never care because we don't do a lot of iterations, but in general it should be done. And the variance of the rewards must be finite. This is also something absolutely reasonable. So the rewards in general are bounded or are fixed value. I said before, remember this term, because when we move to Q-learning, that is a famous algorithms proposed by Watkins and Diane, what we obtain here is exactly the same thing as before, but here we have a max. Why? Because these researchers asked themselves a question and they say, why do we have to select an action? Why? The reason is that we have to select the action that maximizes the Q. So when we are in a state, we want to find a way to go to move to another state where the Q value is the highest possible. So instead of taking a generic action, why don't we select the Q value that is maximized by the action? So considering all possible actions, instead of taking one Q value corresponding to a generic action, we take the maximum Q value corresponding to a specific action. Because when we do it this way, we accelerate the learning process. Because at the beginning, the two algorithms are normally the same. But after a while, the Q function will start to become more and more structured, at this point, when I use the max operator here, I will select the next value given all possibilities. So I will select the so-called next best action. In this way, the algorithm will converge much quicker than normal SARSA. So that's why Q-learning has been used for many applications, from the famous Atari games and so forth, and while SARSA has been not used, because this modification that is, I mean, almost the same, here we don't have the max, here we have the max, that's only the difference, but this difference can make a complete, can drive to a complete different result. At this point, we have the last topic, but I think that probably the time is over. I would like to ask Ghaith to confirm if I can take other few minutes, or
Go ahead.
okay, perfect. This is the last topic. It's called it's another approach. Right now, we haven't searched a policy in a direct way. So we have searched a policy through proxies, Q function, values. These are proxies of the policy. The policy doesn't exist. And by the way, if you look at here, and if I ask you, where is the agent? The agent is the policy, and the policy is the agent. So the famous agent that we have discussed at the beginning is the policy, and everything is embedded into this function. But there are also ways to perform a direct policy search. I want just to show you very quickly a way that is called policy gradient. There is an example in the repository that we'll share, and based on OpenAIG, that can be easily trained in based in TensorFlow, so you can experiment. In this case, we have a parameterized policy, a neural network. Normally, the set of parameters represents whatever you want, but in general, it's a neural network. A certain number of states. In general, the number of states can be infinite, or a very large number of discrete states, doesn't matter. Can be also a set of infinite states in general, but normally all the movements also when the system is continuous can be discretized. And a transition probability from the state I to the state J given a certain action. So at this point, we can define the probability of a certain sequence, S1, S2, S3, S4, Sk, okay, a sequence. In this case, we are not considering a single step, but a complete sequence given a policy. So we have to observe the complete sequence in this algorithm. We cannot just learn step after step, but we have to observe the whole sequence, and then we have to apply a learning step. In this case, this is obtained by considering, first of all, the probability to be in the first state, and it's just as multiplication of the probability of the transition from I to I plus 1 times the policy value of the action A given the state I. In other words, the first term is the weight, the second term is, the second term represents the weight, while the first term is the actual probability of the transition, but the first term, the second term is the weight, because it's the probability that a specific action is taken while we are in the state I. But don't care about this too much in this moment, because we are going to manipulate this in the next slide. So first of all, let's define a cost function. And the cost function is this. Given this probability time R as t, R is the sequence of rewards of the sequence as t, we can compute the summation over ST of all possible sequence of the probability of the sequence times the reward. This is a cost function, and this is absolutely unmanageable. The reason why this is a cost function, it's easy to understand. If we maximize this value, we maximize the probability of obtaining a policy where the reward is high, and the probability to find a policy that will help in finding the sequences or in managing the sequences, obtaining the highest possible rewards. But unfortunately, this is completely unmanageable. We need, first of all, to discretize this. And this is not a problem because the sequences are normally finite. So it's enough just to transform this expression into a sum where 1 over n is just the average value of all possible sequences that we have observed. At this point, what we have to do is just to compute the gradient. Easy. We compute the gradient of L, and we perform a gradient ascent because we have to increase, in this case, this value. But there's a problem. What the hell is this? I mean, how can we compute this gradient here? This is extremely difficult to do. Now, the solution is indeed very simple, because given this complex gradient, this is a multiplication where ST is in both terms, so it's not a simple term. But we can apply this simple rule. If we have the derivative of a function, we can perform this transformation. Okay, these two terms is 1. Okay, this is the derivative of the logarithm of the function times the function. Okay, this is a very simple calculus transformation. So we can move the gradient inside by using this transformation. So the function that is outside is removed, and what we get, we have p, we have log gradient of log p time r. But at this point, we can put this element out, and we can compute the gradient of this one. This one is not, the gradient is computed only on this element, and we can perform, this is possible to prove that is mathematically correct. This term here is just an average. It's just an average because this is a weight. So this is the average of all possible sequences. So what we have to do is only to compute the gradient of the logarithm of the policy multiplied times the reward. Once we perform this operation, so we collect a sequence, we get the rewards for each step, we take the neural network that obtained the sequence, we compute the log of the output, and of course applying the states, the action and the states as in the sequence, we compute the gradient, and we correct all the values by increasing the gradient. So we are not, in this case, reducing. By performing this on this loss function, the optimal policy can be found. So we can find the policy that is like in the classical neural network, optimal, or at least very close to the optimal policy. This is an algorithm a little bit more complex than the others and requires some more details, but I wanted to show you because I wanted to give you a brief idea of how it's possible to solve problems also in reality. This algorithm is called reinforce, like reinforcement learning, but only with reinforce. Now, just 1 second, I want to, sorry, let me, I think I'm showing my screen right now. Okay, in the repository, you will find source code associated to a book. And I want to show you just as the time is over, the SARSA example.
Giuseppe,
Yes.
just I think you are sharing the presentation only, not the full screen.
Oh yeah,
So I think we'll have to
I have to stop and share again the other window. You're right.
exactly.
This is the last thing, and then you are free to go. I'm sorry, I have to show the last slide because. Okay, so don't worry about it's very easy to follow the code, and I will show you after running this how it works. It's helpful to run this. So we have, this is a previous example, sorry. We have this environment. This environment is a labyrinth, okay? Unfortunately, the position of the labels is not perfect. I'm sorry for this, but we start in general from this state, 0. Oh, sorry. These are -5 are considered as like wells where you can fall in. This one here is the final state with 5. All the other states are -0.1 as reward. The goal is to find an optimal policy, starting from each of the states. So we start from the values. In this case, we want to show the values in SARSA. If you remember, we use the Q function, but we show also the value in this case automatically because it's easier. And the value is 0 for all the states. We are not assigning any value. The states that are here -5, sorry, -5 are not classified because in this case the game ends. I mean, it's over. It's like a well where you die. This is the policy at time 0. As you can see, the policy is completely random, and it's not random. Every action is towards up, but it doesn't matter. These are the states, the values, sorry, after 20,000 iterations, and you can see that the values are, it's not immediately easy to understand, but you can see that here the values in this area are quite negative, while will become much larger while we get close to the end. But this honestly is not very easy to understand immediately, but it's much easier to look at the policy. If you look at the policy, let's start from here. Do you see my mouse? I suppose yes. You can find the situations where you can move and you always reach the end. If you see the algorithm, in some cases, the algorithm can find not very optimal solutions, but in general, will reach the end. So we reach always the end. If you start and you follow the path, you can go down, 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 down. Unfortunately, the arrows on the first row cannot be seen, but if you trust me, in general, you try to avoid. If you see when there are the wells, the algorithm now is able to avoid them. Imagine that you are arriving here, instead of going in this direction, you always, or here, you always go far from the well, and you try to go to reach the destination. But again, this is possible to train this algorithm. It's possible to do the same with Q-learning. Q-learning, it's a little bit faster, but it's exactly the same thing. It's the same environment. So you will have the same results, initial point. This is also better in terms of visualization, likely. And you can see also in this case is even better. With only 5,000 iteration in this case, we got a much better policy. You see, starting from each state, you always avoid the wells and you always reach the destination. Okay, the time is absolutely over. In this repository, you can find a lot of source code for all the algorithms, SARSA, Actor Critic, There is also a Q-learning based on, this is quite long, I cannot show you this because I must be trained using TensorFlow, but it's based on OpenAI, so it's the famous pendulum, and you can experiment all the algorithms that we have presented. Just before ending, just 1 second, because I need to show you the last slide. So the last slide here is a thank you and sorry for the boredom that for sure you all have till now accepted. So thank you very much, and I stop sharing and I return to you, Ghaith.
Okay, thank you, Giuseppe. In fact, I enjoyed. I enjoyed very, very, very much. I will ask you to stay with us just to check if there is any question from the audience. Please, anybody on the Zoom with us, he has any question, please raise it right now. There is one question from Mohammed Qasim. Why do we need to balance exploration and exploitation in Q-learning?
We need to balance because, again, Q-learning has not the ability to auto-select the actions. If you use Q-learning, you can think about the example before, and if you start following the policy, you will probably find a path to the destination, but you will only find a single path from a certain point to the destination. So you need always to balance exploration, to explore the different possibilities, to learn also. And remember what I said at the beginning, you can repeat any number of times. And this is an extremely important point. You have to repeat a certain number of times, making mistakes, because by making mistakes, you lower the value of some actions and increase the value of the other ones. And then when you exploit, you reinforce the actions which already have been considered as good.
Vico, thank you for sharing, Giuseppe. I would like to ask about which algorithm is the best one for the online policy reinforcement learning, perhaps.
Well, we have discussed just the beginning of the policy of this algorithm called the reinforce. There are many variations for reinforce. This is a very advanced topic. Reinforce is a good algorithm. There are other versions that can reduce the variance of the estimation that are based on different kind of gradients. So I will suggest to use reinforce, which is extremely easy to use, and to learn, for example, the baseline subtraction algorithm. That is a way to reduce the variance. But this is a very advanced topic. Honestly, I cannot answer very quickly. So I can give you a reference of some books where you can find all the answers, but this is very advanced. But if you apply that algorithm, if you run the example that is in the repository, you can understand how the algorithm works, and you can have an idea. Share the PPTs, of course. The PowerPoints, yeah. Of course, clearly it's not very precise. I mean, I don't like to share something that is not perfect. I mean, but yeah, I will do for sure.
Okay. So thank you. I think there is no other. Thank you. Okay, everybody is thanking you right now, and I personally thank you for this session. It was a great session. I also expect that with 1.5 hours from your side speaking, it's very hard for you. Really thank you. The session was great. It's amazing, and it will be on YouTube for reference for everybody who wants to start understanding the reinforcement learning. Thank you, everybody, for being with us. Giuseppe, if there is anything you want to say for everybody at the end, it's open for you.
I'm glad again. Thank you for the time. It was a little bit longer than expected. Unfortunately, I mean, the topic is very huge, but for me, it was a pleasure, and I hope that it was also pleasant for all the people that participated.
Okay, thank you, Giuseppe. And I think we will meet next month I don't know. I hope with Giuseppe also and all the colleagues. Next month, we have also another plan. We will try to announce it later. Thank you, everybody, for joining us and have a nice weekend.